And I thank the organizers for having the nerve to let me speak here. Because really what I'm going to do is not talk about a reconstruction of quantum mechanics, but maybe an idea for a reconstruction of quantum mechanics. So I want to lay enough stuff out so that you guys who can actually prove things as opposed to me might say, oh, that's an interesting structure to play with, and maybe I can add to the program. Those of you who know me will notice something odd, I think, about my title here. Nowhere in there do you see the word Bayesian. And actually, there's a reason for that, because, you know, I usually have titles that have Bayesian this and Bayesian that, and at the end... Oh, thank you. That's a nice compliment. The reason I've come about this title is because usually at the end of my talks, all the old guys come up and talk to me. But one day, flippantly, I gave a talk at Rob's, or a partial talk at one of our Quantum Foundation's group meetings, and I titled it My Favorite Convex Set, and to my surprise, at the end of it, all the young people came up and talked to me. So I said, that's a winning strategy. But to take it one level further, I have to tell you a story about my 7-year-old girl, Katie. She, from time to time, over the last 2 or 3 years, she's been asking me what's my favorite color. And I always say, blue. Then, you know, 2 weeks later, she says, Dad, what's your favorite color? And I say, blue. One day, though, she said, what's your favorite shape? Just recently. And I was just about to say, a ball. But I caught myself, and I said, Katie, that's a wonderful question. What's my favorite shape? My favorite shape's Hilbert space. and then she said, oh, what's it look like? And I said, I don't know. And she said, well, why is it your favorite shape then? And I said, well, we know enough about it to know that it's really beautiful, even though we don't know the actual shape yet. And then I said, that's what I do every day when I go to PI. I work on trying to find this shape. And the great reward is, about a week after that, she started saying that she wanted to come work at PI. So anyway, this talk is about the beginnings of a reconstruction of quantum mechanics. Everything that I'm going to say in this talk is said more loquaciously and a little bit more rigorously, and with some more steps added and extra assumptions added in this paper that I recently wrote with Rudiger Schock. Rudiger is in the process of writing an intelligible version of it. In other words, he's going to compact the 66 pages of it to about 12. So maybe, you know, that's coming soon, the Rudigerized version of it. But like Lucien pointed out in his opening remarks, it's not even clear what we mean by quantum theory when we say we're going to reconstruct it. So I thought it's worthwhile for me to say a few words on what I mean by quantum theory. This is the end point of a journey that started somewhere in about 1983, or this is the present point of a journey that started in 83. And here's what I mean by quantum mechanics. If you want to know a little bit more of why I've been pushed in this direction, hopefully Chris Timpson will give a talk criticizing at least some steps in this. But here's the vision of what quantum mechanics is about. And it's going to be the thing that motivates the potential reconstruction of it. When I open my textbook, when I open my textbook and say, I'm going to use quantum mechanics, here's what I think I'm doing. At that point, or an experimentalist or a theoretician or anyone who's going to use quantum mechanics, when they use quantum mechanics, they separate the world into 2 or 3 pieces. One piece of the world is me. So I'm the guy who's going to write the equations. I'm the guy who's going to make the predictions. And I assume fully one piece of the world is me. But then there's another piece of the world that is external to me. It's out there. It's a piece of the world that I care about and that I'm talking about. So there's me, and then there's something outside of me, and then perhaps there's some other stuff represented by all these little white pixels That's stuff that I don't care about. But the main idea is that there's me, and then there's some stuff out there. And from my point of view, or this quantum Bayesian point of view that Carl Caves and Rudiger Schock, and to some extent Marcus Appleby buys into, I'm not sure how much Marcus does, but Caves and Schock and myself, we say what quantum mechanics is about is this. I can contemplate taking actions on the systems external to me. Here's my hand. I can do something with my hand on this system. In the formalism, an action on the system corresponds to a positive operator valued measure. So for each action I can take on a system, there's some POVM that characterizes that mathematically. As a consequence of my action, my interaction with this thing, it leads to an experience for me, the person who's performed the action. And I captured the notion of the experience it leads to by one element of this POVM. So this represents an action. This represents the generally unpredictable consequence of the action, or the experience that it leads to for me. This thing called a quantum state is what I calculate my degrees of belief about the consequences of this action. Here's the consequence, here's the action. I don't know which one is going to occur. This thing called the quantum state represents, or is the tool by which I calculate my degrees of belief about what will happen. In this point of view, this thing called the quantum state, if I can think of it as a property at all, I don't think of it as a property of this. Instead, I have it drawn very close to this guy's head because I think of it as a property of him. It's a function of the agent. So a quantum state is not a function of the system, as one normally thinks of when you take, let's say, this dynamical picture that Alex was talking about, option number one. There, one usually thinks, well, there are some properties of this thing, and maybe among those properties is the quantum state. From this picture, this is solely a function of the agent. So that's the point of view here. Quantum mechanics, the whole package of it, is a calculus for ordering and organizing our degrees of belief and making sure that they mesh with each other in a certain way. And it just so happens that the way that they mesh is by using the usual apparatus that we have, that our states of belief are captured by these things called density operators. These density operators live in linear vector spaces based on complex vector space, yada, 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 convex hull. You guys know all this stuff. Now, when one says this, and you take this point of view, that it's about me and the stuff out there and organizing my degrees of belief, the first thing you should ask is, why reconstruct quantum theory at all? Why not just accept this and say, oh, we're very instrumentalist, we're very operationalist, and the world is just that. That's what we do. Well, the thing that's hidden in doing this is that by choosing one calculus for organizing our degrees of belief over another calculus, or over still another calculus, we're making an implicit statement about the character of the world. I could say an implicit statement about ontology. Ontology seems too foo-foo for me. We're making an implicit statement about the character of the world by choosing this calculus, perhaps over some other calculus. There are many possible calculuses, and for instance, the test-based formalism gives a whole load of potential worlds, or the convex structures approach gives a whole load of potential worlds. And these worlds, based on different convex sets, lead to different statements about the ultimate character of the world, what the world is made of. So the point I just want to emphasize is that even if one takes this point of view that it's about my degrees of belief and about my experiences, from the calculus that we use for making our decisions, we can still distill some statement or some information about the character of the world without me, or at least we should be able to in principle. The end point of this program, because I would like to know about what the character of the world is, or the best I can say about it, would be this. So when I reach my nirvana at some point, there will be no quantum state psi in my picture. Why is that so? Well, the reason that's so is because I've already got the point of view that when I write down a psi, I'm talking about a property of me, not a property of it. And what I'd really like to do is make some statement about the properties of it. So that's the end point of the program. Now the question, or one question, is how to get there. And that's what the remainder of the talk is about, is maybe potentially a first step in going in that direction. Here's what I want to do today, or the direction I want to take today. I want to explore this thing called the Born rule, which is, we usually state it as, suppose you're given a quantum state and you're given some POVM, and you want to calculate the probabilities for the outcomes of the POVM, then you use a simple rule that had its precursors in Born. And much of the restructuring program that I've seen usually relies on the idea of trying to specify what we mean by this. Let us give some structure for what measurements we can make, and then we might try to derive the Born rule. So the Born rule is not an axiom of quantum mechanics. It's something derived, say, for instance, from Gleason's theorem. So we're given the structures of measurements. That's the basic thing we're given. And then from the structure of measurements and some assumption about the non-contextuality of the probability assignments, we get the Born rule. The Born rule is a theorem. Well, what I'd like to do is take the Born rule as an axiom instead, and get this other structure, these two things, from this as an axiom. But what's really lying behind this is a further belief that has to do with this whole Bayesian business that I didn't put in the title. And that is that this thing called the Born rule is not really a law of nature. You shouldn't think of it as a law of nature, something that God laid down and nature must follow. Rather, we should think of this in a normative sense. In a normative sense in that it's something we should strive for. The Born rule is something you aim for, something that you would like to ideally do. Now, what do I mean by that? Maybe a good example comes from the Ten Commandments. I thank PI for lending me a plate yesterday, so I could get that rounded part. There's the Ten Commandments. Thou shalt not kill. Well, okay, the commandment says you shouldn't kill, but you can still do it. You can go out and you can kill all you want. What it tells you is if you kill, something bad will happen. Beware of that. Thou shalt not steal. You can steal all you want. It's not that the world says, or the world makes it so that you never steal. You can steal, but something bad will happen. The firstling of an ass thou shalt redeem with a lamb. The world doesn't make you do that. You could break that one. But if you do, something bad will happen. Bill might explain it to us later. I don't know what it means. So let me give you a more technical sense of this idea of thinking of the Born rule in a normative way. And I use as my icon the Bayesian development of probability theory that goes back to Ramsey and DiFinetti in particular. So what these guys did was they, at least tentatively, they defined probability in terms of betting, something that Luca Manna hates. Luca's not here. Well, it seems ugly because it involves money, but bear with me. Probabilities are defined in this way, in this setting. This is called the Dutch book definition of probability. When a bookie over here posts some probabilities for various events, probability for event E, probability of not E, what he has done is he has declared a contract that he will buy or sell lottery tickets of this structure, a lottery ticket that's worth $1 if E. He will either buy it, he has to buy it if you try to sell it to him, or he will sell it if you try to buy it from him for this much money. So all this number means is this is what he will buy or sell the lottery ticket for. And this is taken just as the raw definition of what probability is. Now, I think there's just simply no structure here because, how you buy and sell depends upon you, and there's and all kinds of factors. But to this, if we want to get some structure, we add something that I'll call a normative rule. That is, that the bookie should never declare probabilities, P of E, P of not E, P of E or F, etc. He should never declare ones that will lead to a sure loss in one trial. He should protect himself at least that much. Yes?
So,
if it's short and meaningful.
and you can postpone it if you want, but you're talking about, you use money, but you're assuming then sort of a marginal utility, constant marginal utility. I keep trying to say, well, that doesn't matter, but it seems like it does, because everything is subjective here.
Here's what I hope you'll grant me. I'm giving a bit of a cartoon version of the Ramsey and different eddy development. Ultimately, one really needs to speak about utilities or give some justification for why one's talking about linear utility. So we're talking about little increments of money. We're not talking about American dollars, good, strong American dollars, but we're talking about Mexican dollars, something like that. So one can certainly get much more complicated on this, but I want to give the flavor of what it means to be a normative rule. So that's why what? Oh, I thought it was Howard. They used to. Because I found some in my drawer recently, and I found out that there were dollars. I didn't realize this. Okay, so the bookie should never put himself in a situation where he'll have a sure loss. For instance, I'm going to give about 5 examples of this to really just put it in your brain, and then we'll move back to quantum mechanics. Suppose that the bookie wrote down a negative number for the event E. Well, what that would mean by the definition is that he's willing to sell a ticket for negative money. In other words, he's willing to pay you to take the ticket off his hands. And if he does that, regardless of which outcome occurs, he has lost money. So this tells us that probabilities should be greater than or equal to 0. Alternatively, suppose that he has written down a number P of E that's greater than 1. Well, by the contract, it says he will buy a ticket for more than it's worth, because in the best case, the ticket's worth $1, and he will buy it from you for more than $1, so he has a sure loss of money. So we now have the probabilities, just from this normative requirement, have to be between 0 and 1. Where does one get, for instance, the additivity of probabilities? Well, take this ticket, worth $1 if E or F. Well, the amount the bookie will buy or sell this ticket for is P of E or F, that number there. Consider that in relation to these other 2 tickets, worth $1 if E and worth $1 if F. Clearly, the value of this ticket had better be the same as the value of these 2 tickets. Otherwise, someone could come up to the bookie and sell him the one and buy the other 2, or vice versa, and lead to a situation of sure loss. So he had better adjust his payment scheme so that these 2 are equal. Just as a homework problem, and because I'm going to need this for the next step, consider tickets of this structure. It's worth M over N dollars if E. So where I don't have a $1 here anymore, I have M over N dollars. You should try to convince yourself after this talk that the price he should charge for this, lest he run into trouble with this one up here, is this, M over N P of E. Let me give you one last example. Where does Bayes' rule come from in this normative setting? To get Bayes' rule, you consider conditional lotteries. So these are lotteries of this structure. If E and F, give the full price of the lottery ticket. But if F doesn't occur first, return the money. Okay, so you buy this. I should have had a red box around this because this is a ticket. And the amount that we're going to pay for the ticket, I'll denote by this little symbol. So give the full price, give $1 if both of these guys occur. But return the money if F itself doesn't occur.
You mean the full payoff? If the price of the ticket is
Oh, yeah, full payoff. I'm sorry. Yeah, that's even more confusing. Sorry. So forget about this now and look at this one. I think I've stated it more carefully here. It's worth $1 if E and F. It's worth whatever you paid for it. Whatever you paid for it, if not F. I'll just look at that ticket and compare it to these two tickets. Worth $1 if E and F. Well, that's what you would pay for it by definition, or buy it for. And it's worth this much, this one up here, this much, if not F. Well, again, the same situation that we had on the previous slide. The value of this ticket had better be the same as the value of these two tickets, otherwise someone will have a sure loss. So it has to be the case that this number equals the sum of this one and the sum of that one. We've scaled. Remember, that's why I showed you the lemma. And then if you just do a little bit of algebra, you get this thing that's normally called Bayes' rule. Okay, so where does the structure of probability come from? It comes from a definition of what you do with the probabilities. You buy and you sell. And it comes from a normative requirement that says, if you're stupid enough to not adjust your probabilities so, then somebody can take you for all you're worth. Yeah, for instance, to get from here to there, you need an invocation of just regular, plain old Depression-era logic. Yeah. Well, but again, this is not what people actually do. So, I mean, you hit on a point here. This requirement here, oops, this thing, is not something that people necessarily actually follow. People break Bayes' rule all the time. People are incoherent, this is called, in this sense, all the time. But this is what they should do. For instance, suppose we have a gambler who contemplates buying or selling, an F ticket for this much money, and a conditional lottery for this much, and a joint lottery, for that much. You take these numbers, you multiply them together, you don't get Bayes' rule. Now, that doesn't mean that there is some compulsion in nature that would cause him to not gamble that way. He could gamble that way, but it wouldn't be too wise, because if he's not coherent, a Dutch bookie can take him to the cleaners. So the idea here is that one should strive for coherence. It's an ideal. What does it have to do with quantum mechanics? I'd like to give a reading of quantum states in this normative way. Instead of thinking of them as things that are out there, or indeed thinking of them as things that people actually use. Instead, they are things that people should use if they want to build the best life that they can in this world. And the way I'm going to do it, or at least the way I'm going to explore the issue, is to first get rid of the calculus of quantum states and replace it with the calculus of probability theory, full stop. So I'd like to rewrite things like the Born rule in terms of straight-up probabilities, and then look at the structure that comes about. And this transparency you guys have seen for, many of you, for 7 or 8 years now. But you can see it's getting old, poor fellow. It's a little bit missing up here. And the way I'm going to do this is, here's a quantum system. I'm going to imagine a very special measurement device that I'm either going to lock away in the Bureau of Standards, or I'm going to put it up in the sky where we never really reach it. So here's a quantum system. We normally describe the quantum system in terms of quantum states, but what I want to do is put this measurement device, this very special measurement device, up in the sky, and I want the measurement device to be informationally complete. so that if I knew the probabilities for the outcomes of this very special measurement device, I could completely reconstruct the quantum state. Well, by doing that, then I've just by putting this in the background, I've stopped talking about quantum states as operators, and I now just think of them as probability distributions with respect to some very special measurement. What's the special measurement? There are all kinds of measurements one could use. Yeah. Yes. Everything I'm talking about in this talk, this is the beginning of a reconstruction. So, you know, the nasty question I asked Alex was, would you be happy if you could just reconstruct a Q-trit? Maybe the reason I asked that was because I'd be pretty happy if I could just reconstruct the Q. I got the Q-bit already. I mean, if I get the Q-trit, then I think then I'm pretty much there. I mean, I see what to do, you know, all the rest of the way. So, yeah, everything in this talk is going to be about one system of a fixed finite dimension. Call it D. D for dimension. So which measurement device am I going to use? Well, there are many that one could contemplate, and I think the earliest precursor, I was thinking about this recently, for this idea, for me, was a paper that Bill Wooters wrote in 1986, apparently, that I read. It was in a special issue for John Wheeler's 83rd birthday, I think, Foundations of Physics. And he proposed writing quantum states not as single probability distributions, but as tables of probabilities. And he made the remark that there are many bases that one could use. You just need a complete set of bases. But some bases are prettier than others in the sense that they may give rise to simpler formalisms if you choose your basis appropriately. So for this quest, I think there is one outstanding candidate for what should be used. This is a measurement that I think Gerhard Zauner was the first person to think about. He wrote his PhD thesis in 1999, and at a meeting in Cambridge, England in 1999, Carl Caves also thought he needed a measurement of this flavor so that we could prove the quantum Diffie-Hellman theorem. In the end, we didn't need it, but the question stayed around. Can you have a measurement of this flavor? Suppose you have d-squared rank 1 projection operators that satisfy the condition that the Hilbert-Schmidt inner product between any two distinct ones is a constant, a particular constant. So you've got d-squared of them. Well, this particular constant is the only constant you could have if you actually had d-squared of them. So that's what you need. Suppose you have d-squared projectors satisfying this, then you can prove two things. One, it follows from this that these pi i's must be linearly independent operators. The other thing that follows is that if you equally weight them by 1 over d and sum them up, you get the identity. So this is an example of the sort of measurement that you would need for the Bureau of Standards. You have d-squared operators. They're all linearly independent, so they span the whole space of operators, and they lead to a measurement because you can sum them up and get the identity. So it's a good measurement to use for up there. What's really nice about it, and we didn't realize this until much, much later, because we weren't thinking about these Bureau of Standard things back then, was that if you look at the formula for reconstructing the quantum state from the probabilities, it's just absolutely simple and trivial. And it's the only measurement with d-squared outcomes that gives such a very simple formula. It's just a little affine transformation on the and you know, a very simple transformation on the terms. Generally, you would have some extra matrices in here. So you'd have a pi I and then a mij on the inside, and it wouldn't be just a diagonal matrix. Okay, so this I'm going to take, and at least initially, the motivating reason for thinking about this particular measurement to use in the Bureau of Standards is because it's immensely simple. And where there are simple things in the background, one may end up with simple conclusions, and that's what we want. Well, do they exist, these things? That was the big question in '99. When Caves dreamed up the question, he could see that they existed in dimension 2. Because you just take a Bloch sphere and you take a regular tetrahedron on the Bloch sphere, and that's the measurement you need. So then he came to my office and said, do you think these exist in arbitrary dimension? And I said, I don't know. So we thought about it for a day, and we didn't get anywhere. The next day we went to Bill's office, and Bill said almost immediately, I think they exist in dimension 3. And he quickly worked out this set on his, I think it was this set, on his chalkboard. So they exist in dimension 3. That was a good sign. Since then, we know a lot about dimension 3. I think this is another set. I think this one was invented by Robin Bloom-Cahout. So anyway, they exist in dimension 2, and they exist in dimension 3. And I'd like to say that they always exist, but we don't know whether they always exist. What is known, and I think Marcus Appleby in the audience is the world expert on everything that's known about the existence of these things. They, for sure, because of analytic constructions, they exist in dimension 2 through 15 and dimension 19. These numbers have been changing a little bit. Some of these analytic constructions, dimension 2, 3, 4, dimension 2, 3, and 4 are just do the algebra by hand. Starting around dimension 7 and 19 are examples that Marcus found just by guessing them, by really clever guesses. A lot of these, when I say they're analytic constructions, it's because Marcus Grossel has set Magma, this computer algebra package, on the problem and let it churn until it generates a solution. Andrew Scott has done a lot of numerical work recently, and he's pushed out the numerical solutions out to dimension 67 with a very small factor of error. So in other words, we can satisfy these constraints very, very tightly, at least out to dimension 67. At that point, I think his computer runs were lasting like 2 or 3 weeks to find a new solution in the next dimension. So at that point, he gave up. But I think most people, I don't know if that's true. If you talk to a combinatorialist, I can't remember the guy's name at University of Waterloo, he says, well, this doesn't mean anything to me. But I'd say most physicists probably believe that they exist, just from this evidence. So for the rest of the talk, I'm going to assume that they do exist. And I'm going to talk about what quantum mechanics looks like in terms of them. Well, the first thing that they do is they give you the opportunity of representing a quantum state as a point on the probability simplex. We've said that before. But here's where interesting things come in. This mapping is one-to-one. Once you introduce one of these fiducial measurements, one of these measurements in the Bureau of Standards, the mapping is one-to-one, but it's not onto. So there are points on the probability simplex that don't correspond to valid quantum states. So you can go from a quantum state to a point on the simplex, but not vice versa. What they generate is a convex set, as we've heard so many times. If you use these very symmetric measurements, which, by the way, have become known as symmetric informationally complete measurements, SIC, which I've gotten in the habit of calling SICs. A SIC. SIC is a SIC. What do quantum states look like in terms of these? What does this region look like in terms of these SICs? Let me just give you a quick description of it. I'm going to use this thing that I call the remarkable theorem of Steve Flamia and I think it's Nick Jones and Noah Linden. If you have a Hermitian operator, Flamia and Minicucci. I'm sorry. She knocked me off track. A is a rank 1 projection operator if and only if the trace of A squared is equal to 1 and trace of A cubed is equal to 1. Well, okay, so if you're one of them, I should say why I call it a remarkable theorem. So I call this the remarkable theorem. I wasn't going to tell this joke this time. But I call it the remarkable theorem because, to my shock, when I first heard this, I thought, God, I should know that. The proof of it is really trivial, really easy to work out once you've been told it. I thought, well, I should have known that, but I guess I didn't. But, everyone else must have known it. Well, Carl Caves didn't know it, and then I found out that Alexander Holovo didn't know it, and I found out that Goran Lindblad didn't know it, and I found out that Beth Ruskay didn't know it. And you know how I found out, because I'd go up to people at coffee breaks and ask them, hey, did you know this theorem? And Elliot Lieb didn't know it, and I'm not making this up. So I started thinking, wow, this is about as surprising as the no-cloning theorem, which surely could have been found, anytime between 1927 and 1980. But it seems like people just missed it. Well, similarly here. So I'm going to use this characterization that if I have a Hermitian operator such that trace A squared and trace A cubed equals 1, then it's a rank 1 projection operator. So what does this region of quantum states look like in this description where you just use the theorem? You let rho be Hermitian. In other words, you just write down the form that I had on the previous transparency, and you by hand force the trace rho squared and trace rho cubed equals 1. And so the condition is, once you translate these equations, you get two equations, that the sum of the pi squareds is equal to a certain constant, and then that's the quadratic equation. And then the cubic equation is that you get this combination of probabilities where you get this nice, completely symmetric 3-index tensor in the middle. So here's the point. The space of quantum states in this language is the convex hull of this algebraic variety, whatever this algebraic variety is. If you can give some motivation, let's say, just from the raw Born rule, that ultimately leads to a convex set of this structure, then you've come some way toward a reconstruction of quantum mechanics. You still have to talk about dynamics and this and that. But what I'd like to aim for in the rest of the talk is at least giving some features of this convex set. And sets with that feature I'll call my favorite convex set, or my favorite class of convex sets. So what sort of thing might I be thinking of? Well, let's go back to coherence, just probabilistic Dutch book coherence. And particularly, let's talk about the law of total probability. Suppose the following. We have various hypotheses about something. I'll call them HI, mutually exclusive hypotheses, and various mutually exclusive values for some kind of data that I could be contemplating. Suppose I'm given the conditional probabilities for the data given the hypotheses, and I'm given the prior probabilities for the hypotheses. What expectation should I have for the d sub j? In other words, how should I gamble on d sub j itself? Well, we'd use the law of total probability, regardless of what your axiomatic foundation for probability theory is. In my own case, I'd say, well, this comes about just by another application of the coherence idea that we had before, where you can just bootstrap what we talked about before into this. And it tells you, well, the probability assignment that we'd make for the dj is just, we just take the prior probability and multiply it by the conditional and sum over all possibilities for the hypothesis. And that's the law of total probability. Comes about because of coherence. Well, what if we tried to apply it to this situation? This situation is not just talking about propositions, etc. Now we're talking about quantum measurements. And here's what I'd like to do. What I'd like to get at is what probability I should assign to this measurement device, a measurement device that I'm going to say is sitting on the ground. This measurement device on the ground, what probability should I give for the outcome, J? Given that I don't have a quantum state for it, and maybe I don't even have a description of which measurement we're talking about here. The only thing I have is a promise that it's a von Neumann measurement. So I mean by that a complete set of rank 1 projection operators. So I'm given the promise that I've got a quantum system and I've got this von Neumann measurement device, but what I'm given instead are the probabilities for the outcomes of a seek up in the sky. So this is my Bureau of Standards measurement. And I'm also given the probabilities for the outcomes dj down here, given hi, went off the side. One of these days I'm going to start drawing things on my screen so that this doesn't happen, but I still do it on transparencies first. So this is P of dj given hi. So I use the law of total probability. In other words, would I just say, well, the probability for getting outcome j over here, if I go this path, this real path, is just equal to the sum of P of I times P of dj given hi. Well, no, I wouldn't. And the usual explanation for this, which in my opinion is no explanation whatsoever, is people say, well, this breaks coherence. You ask them, what does that mean? Well, I don't know. Maybe it breaks Dutch book coherence. Maybe that's the point. No, you wouldn't use the law of total probability. But what is so special about the seek up here, as opposed to any other informationally complete measurement with d-squared outcomes, is that you actually can calculate the probabilities for this path in terms of that path. It's a very simple function. It's just that. And that comes about because of the expansion that we had previously. So the probability for outcome dj, well, the first thing you do is you do what the Bayesian would have done, not thinking about quantum mechanics. And then you distort it ever so slightly by a factor that depends upon the dimensionality of the Hilbert space. So you get this very pretty formula. And I find that motivating. That finally, a pretty formula in quantum mechanics that involves only probabilities has come out of the wash. Well, you can generalize this sort of thing. Remember, if you go back here, the measurement on the ground was promised to be a von Neumann measurement. And this is any seek. This is any von Neumann measurement. And that formula always holds.
I need something clearly. Why doesn't this violate special coherence? I mean, why are we departing from the usual case?
I will come directly to that after a little bit more work. So, yeah, that's a very good question. And it's part of the presentation. So where was I? So the point is that this formula is universal. It doesn't depend upon which seek we've talked about, and it doesn't depend upon which von Neumann measurement we're talking about. It always holds. But it did require the promise that we're talking about a von Neumann measurement on the ground. You can generalize it. So suppose you have any measurement up in the sky and any seek on the ground. Well, the formula is almost the same except for this factor changes. And more generally, if we now really want to talk about the whole shebang, you still have the seek up in the sky, but now we allow any measurement, any POVM whatsoever on the ground, then the fully general formula is this thing in red. It's got a piece that looks like the law of total probability with the same multiplying factor that we had before. But at the end of the day, we have to subtract a term that's the sum of the conditional probabilities, where I sum over the various hypotheses. What I'd like to start toying with, well, let me not tell you about that. Let me answer Ariel's question first. Here's what you notice. This is not the law of total probability. Should we be troubled? Should we be troubled that we have violated Dutch book coherence in some way? And the answer is we shouldn't be. And it's precisely for the reason that Inge Helland in his talk was talking about. We have two different experiments. One is the bottom experiment, and one is the one through the top. And the conditions are different between the bottom and the top. So behind these probability assignments, there really ought to be an extra condition. So P of dj given B, P of hi given T, T for top, P of dj given hi and T. So there's no violation of Dutch book coherence because of that. And this has been noticed ample times in the past. For instance, Rob Speckens brought to my attention some papers by Koopman and another paper by Leslie Ballantyne criticizing the way Feynman presents this in his book, because Feynman says, look, the laws of probability are changed. And these guys say, no, no, they're not changed. What's happening is that there's an extra condition, and you're ignoring that extra condition. Okay, so a statistician and maybe, well, maybe a statistician of any stripe would say, oh, there's nothing surprising there because there are extra conditions in the problem. What is kind of interesting, however, is that quantum mechanics doesn't just say that they're not equal and that there's an extra condition there, but quantum mechanics gives a precise relation between this and this. It's just one that we aren't usually accustomed to. So the point here is that there may be empirical reasons for adopting some relation, and apparently quantum mechanics, whatever it is that has given rise to quantum mechanics, has given us some kind of reason to adopt a precise relation between this side and that side. And maybe we should recognize that and go with it and try to use it as part of a reconstructive program. I can't help but tell you about this. I think this is really cool. This word was written all in blue, and yet you see the P being purple. And the only thing I can think of is that when I scanned this in last night, the computer said, oh, this is touching that, and it looks to me like they're different colors, and they shouldn't be. So it changed the color of that. That is so cool. Yeah.
The Bayesian thing, I'm trying to put this together with the standard Dutch book argument. Doesn't the standard one assume that it would be commensurate to using classical outcomes?
No, the standard, let's say the standard one for the law of total probability comes about precisely when you've got this step in the middle. So it says, how do I match up my probabilities for three different situations? One of them is this lottery. This represents a lottery. One of them for this lottery. One of them for this lottery following that lottery. And that's what the law of total probability is about. So as long as you're talking about the top path, you can use all the usual stuff from classical probability theory. Only thing that's new in quantum mechanics is that quantum mechanics gives you a way of comparing the top path to the bottom path, and regular probability theory doesn't do that without extra assumptions. So quantum mechanics is an extra assumption.
I thought the Dutch book argument did assume that absolutely, because you had slides where you had conditional probability changes, and said, I mean, are they not allowed? I mean, are they not valid if you just use that alone rather than or P alone rather than once?
Why don't we come back to this? But I'd say no, it didn't. But I'm going to have to convince you of it, and that might take more time than it might knock me off a little too much off course now. But come back to it. So here's what I'd like to do. I'd like to play with the idea that that is the content of the Born rule, this extra relation, and see if we can get quantum mechanics out of it. Of course, there's one glaring question. In the case of a Dutch book development, it's obvious what bad things happen. In the case of the Ten Commandments, it was obvious what bad things would happen if you didn't follow the commandment. You'd go to hell, you know. And in the case of Dutch book, you would lose money surely, and that's a bad thing. If this is on the right course, then it must be, if it's on the right course, that's a big if. If this development's on the right course, it must be the case that if one's probabilities do not satisfy this relation, the Born rule, something really bad will happen, and it will happen bad even in the single case. Now, I'd like to identify what that bad thing is, and I haven't. But nonetheless, we can still move forward and try to get some mathematics out of this program. One other very general remark, and this relates to some extent to Alex's talk. When a lot of workers in these reconstruction programs view quantum theory as a generalized theory of probability. There's probability theory, and then there's a larger structure, some generalized notion of probability. And within that larger structure, one can recover just probability theory. So probability theory is a subset of this more general structure. This point of view is not that. So everything that I'm talking about here is not a variety of this. Instead, it's a variety of this, that there's a foundation that we talk about before we start any physical theory called probability theory. And probability theory is just about not making stupid choices in your decisions. And that's all it's about. When you apply probability theory to any particular problem, you add extra structure. So for instance, and I think this meshes with Inge's talk a little bit, when you're talking about economics, you add some extra assumptions that let you know that you're not talking about ducks, you're talking about economics. Similarly, when you're talking about your interactions with a quantum system, you add extra assumptions to this raw thing called probability theory, and that's what quantum mechanics is about, is adding extra assumptions. So from this point of view, there is no generalization of probability theory. Probability theory is about as, well, probability theory lives at the level of just plain mathematical logic for reasoning lives. Quantum mechanics is an addition to that. Okay, so here's what I want to do. I want to take this diagram as perhaps much of the basis of quantum mechanics. I want to say that whenever I contemplate doing some experiment on the ground, any experiment, that's why I wrote variable, on the ground, I can reason about it. I can derive my probabilities from considerations to do with a measurement in the sky followed by the measurement on the ground. In other words, I want to play with structures that are of the variety that I should calculate these probabilities as some function of these probabilities and these conditional probabilities. And in particular, to get the ball rolling, I'm going to consider the case that looks very much like we've already encountered. The number of outcomes up here in the sky is a perfect square. The number of outcomes on the ground is still completely variable. That should be an m. But the rule that we use to relate these probabilities to these probabilities is of this general form that we've already found in quantum mechanics. And the question is, does this already have enough structure to tell us that we should be using positive operators, blah, blah, blah? Does it already do that? And how could it do that? Well, for instance, if we want this formula to always work, it had better be the case that for whatever priors we have up here and whatever conditionals we have down here, this number still be between 0 and 1. So the idea that the number on the left should be between 0 and 1 places automatic restrictions on the priors and the conditionals so that that won't happen because there's a negative sign. If this term becomes too large, for instance, Q of j would be negative, and we wouldn't want that. So part of the idea is you get a theory of priors based on an addition to coherence. So normally one thinks in the Bayesian setting, well, there's nothing to stop an agent from adopting any prior, nothing a priori at least. And here we're saying, no, if you have accepted this extra coherence, then it does place constraints on your priors. So let me show you how this goes a little bit. By first considering a property of quantum mechanics, and I think I can stop within about 5 to 10 minutes, and then we'll have the rest for questioning. Here's just a property of quantum mechanics. Suppose you have an initial quantum state that's just the garbage state, 1 over d times the identity. And you actually go through the path in the sky. So you go up to the seek, there's a click, and then you come down to the ground and there's a click. And suppose that only the click on the ground is available to you. It's outcome j for some POVM g sub j on the ground. Well, because you've gone the upper path, you are entitled to use full Bayesian reasoning about everything, regular Bayesian reasoning. In particular, you can say, oh, given that I got this outcome j, what should I believe of I up in the sky? What are my conditional beliefs about I up in the sky, given that I got j? And you can just use Bayes' rule. Well, we had a flat prior on I, and so if you just work out these terms, you find then that the probability that a click I occurred in the sky, given that j occurred on the ground, is just given by trace of this ground operator times 6p of the m element divided by that. If you take these operators, g sub j divided by the trace, you can rewrite it in this form. And so what this is telling you is that this probability of I given j is just the seq representation of this density operator, rho sub j. Well, now you can notice the following. Any rho j, any density operator, rho j, can be gotten in this way by a suitable choice of the g's. So you perform a measurement on the ground. In some sense, by choosing the right measurement on the ground, you can prepare, quote unquote, prepare any state for the sky. There's nothing that you miss in that way. By appropriate choice of measurement on the ground, you can prepare a proper state for the sky. Well, I'd like to take that as an axiom in any system along these lines. In other words, I'd like to say that starting from a state of maximal uncertainty for the sky, one can use the posterior supplied by Bayes' rule, which is just this, to just work it out, as a valid prior. Moreover, all valid priors can be generated in this way. So you let it go through the sky, you see your click, you imagine a posterior for the sky, and the axiom is that your posterior can be a prior. And all priors arise as posteriors. Well, that leads to an immediate consequence. We can just take this expression and plug it into our first axiom, axiom 0, and rewrite it in this way, where P of I is some prior for the sky, and prob I given j, because of this axiom up here, is some other prior for the sky. And we want this to be non-negative, so then it just follows that for any two valid priors for the sky, their inner product is bounded below by a seemingly interesting number in terms of this dimension. So for my priors in the sky, there always has to be some overlap between them, as specified by this. Okay. So now I'm in the realm where I'm talking about valid priors. At least I have some information about what priors I can adopt. No two priors that, if I have a set of possible priors, no two of them can be too far apart from each other, too orthogonal to each other. Let me see if I can establish that my set of priors must contain at least some elements. That's what the next transparency is about. I'm going to establish that there are at least d squared interesting priors that have to be in the set. And the way I'm going to do that is I just consider the case where I make my measurement on the ground, the one down here, the same as the one that was up in the sky, and demand consistency of my formula. So if I do that, then I get if I send a P of I to the sky, the one that I get on the ground is some other P of j, and I just have to have equality between these two sides. Well, there's only one way to satisfy this if these P's span the whole space of probabilities, and it's by choosing R of j given I as this. And now I use the principle of reciprocity that posteriors equal priors, and I get that my set of priors must contain all probability distributions of this form, where they're flat everywhere except for at one point. So these guys have to be in the set as well. Now, just notice one thing, that if I take the inner product of any one of these with itself, I get this kind of interesting number. The reason I'm pointing this out is because at this point I'm going to start taking great liberties and not show you all the details in the paper and all the extra assumptions that sort of carry it through. But I'm just going to say, oh, I like this property so much for these guys that came about just from consistency. I'm going to suppose that it's the case for all extreme states in my convex set. So I can do a little better than that. I can give some better motivated, not much better motivated assumptions than that. But for this talk, I'm just going to assume that. Okay, so now I'm at the point where I can say, I've given you the start of a reconstruction, and this team of guys that I'm working with, Åsa Eriksson and Marcus Appleby and Rudiger Schack and Carl Caves to some extent, we're a little excited about this program. We think that it can be pushed further, but we haven't gotten there yet. And so let me just tell you the broad, like an example of some things that should be considered. Okay, so just two more transparencies. Based on the sorts of things that we've talked about, this is the sort of thing that got the young people to come talk to me, so I hope they still will. We might consider a class of convex sets with the following properties. So let S be, oh, I shouldn't have said convex, because I'm not going to assume it yet. I'm not going to assume it. I'm going to talk about a different kind of structure. I'll call these maximally consistent sets. We'll call it a set S that's a subset of the probability simplex over d squared outcomes, consistent if for any 2 points in that set, the inner products are lower bounded and upper bounded by the 2 numbers that we've already seen arise in this talk. Furthermore, I'm going to call them maximal if I already have a set, let's call it S prime, that is consistent, and now I take another point from the simplex that's not in S prime, and I add it to S, and I check, does it become inconsistent, or does it remain consistent? If it remains consistent, then I allow it to be in my set. And then I take another point, and I throw it in. As soon as I get to the spot where I can't add any more points, then I will say that it's maximal. Adding any further point will make the set inconsistent in these terms. So the sort of structure that I'd like to consider are these things that I'd call maximal consistent sets. Well, okay, now you can just convince yourself maximal consistent sets must be convex sets. And they have to be convex sets is we fix P and take any 2 Q's that satisfy this, then a convex combination of those 2 Q's will satisfy it. And if we make the requirement that they be maximal, then we have to throw those points in. So we have a convex structure arising as a second step, not as a starting point. And here's an example of a maximal consistent convex in that convex set. The set of quantum states have this property. I'm not going to show you why that's the case, but it is the case that quantum states alone already have this property. So the sorts of things that one might like to discuss are, well, what is the general structure of these maximal consistent sets, and how do they compare to quantum mechanics itself? Well, they've already got some features. Of course, I've to some extent built them in. Let me just show you 2 that intrigue me. It's in the following sense. If I take quantum state space and I represent all of the operators as probability vectors with respect to a seek measurement, okay, and I take all of those, then that gives me a convex set within the simplex. And my claim is that if you take any point that's outside of that convex set and attempt to add it into the set, it will cause this condition to be it will cause this condition to be violated. Yeah, that's right. That's right. But one of the beauties of the seek representation is I can just sort of throw away all the negative terms. There's a simple transformation from the probability itself to the coefficients in the expansion, which are generally negative. But here I'm just talking about the probabilities themselves. Now, so quantum state space has this property. Here are a couple of other properties. So we have the requirement, suppose we take our 2 points to be the same, then it has to be the case that for any point in the state space, P dot P is smaller than or equal to this number. You may not remember it, but that's exactly the number that arose from the quadratic condition in pure states. Now here's a more interesting one. I mean, that one was almost built in the way that I presented it today. The paper does it better. Here's a more interesting one. Suppose you have a subset of points in this convex set, any maximally consistent set. We're not talking about quantum state space here, but any of this variety. And we want to satisfy, and we have m of them. We have m points, And we'd like to satisfy this property, that the right-hand side of the inequality is achieved, and the left-hand, whenever I consider the same point, and the left-hand side of the inequality is achieved anytime I have two distinct points. So let's go back here. Oops. Where did it go? Yes. So I'm achieving the upper bound whenever Q is equal to P, and I want to achieve the lower bound whenever I'm talking about two distinct points here. So that's what I'm trying to require. And I ask myself, how large can M be? In other words, how many points can achieve these two things? Well, I'm asking for a set of vectors with a certain inner product relation, and I just write down the Gram matrix for this. And then, lovely, what you find, once you pull things, you rescale the probability so that they're out of the plane, is that this proposed Gram matrix eventually picks up a negative eigenvalue if M is too large. So it turns out the largest value that M can be, just given by these inner product relations, is D. So we had probability distributions over D squared outcomes. And what we find is that the number of points that satisfy these two things, the largest number is D. That mimics quantum mechanics in that it corresponds to the orthogonal vectors on the Hilbert space. So the ultimate question is this: what further postulates must be made to recover precisely quantum state space? And what I mean by precisely quantum state space is the convex hull of this algebraic variety. What further postulates? Well, they have to be postulates that stir me. So if you come up and you say something like, oh, I want a compact group of automorphisms to connect all measurements, I'm going to say, what does that have to do with the Bayesian program? Or maybe it's just my mentality, but I want to have a story that I can write for the New Yorker and say the essence of quantum mechanics is this. So when I'm looking for extra postulates to add to this group, it's got to be something that really gives me an image of what quantum mechanics is about, something that might turn Hilary Putnam around from his later day inclination toward Bohmianism back to something else. Now, I'm not sure what that something else will be, but and I don't know how close I am to getting this full structure. There's a lot of things I haven't exhibited here. Åsa Eriksson, for instance, has been looking at the general structure of these guys, and she's noticed, for instance, that suppose you have a vector P that has some number of zeros in it. You can ask, oh, if this is a valid one, can any permutation, where I've just permuted all of the elements, can that also be a valid prior? And the answer is no, generally not. Because if you take the inner product between the first and the second, it starts to violate our inequality. So you don't have permutation invariance anymore. Well, you can start to make quantified statements of if you have so many zeros, how many permutations must be excluded from the set. So symmetry starts to get broken in interesting ways. So the main point of this is that I think that this inequality in this notion has a lot more structure in it than has already been explored. How close it gets to this structure, I don't completely know. And with that, I'll stop blabbering. Thank you.
Okay, we have 20 minutes for questions, discussion.
Alex. Oh, I'm sorry. No, you're the chairman. You do.
What is your question?
I didn't say my question was absurd. Ridiculous. This doesn't have the flavor of an absurd question.
One can certainly imagine formulating something like the notion of a sequence in some more abstract setting. And then I guess I want to ask the question: why should I? Is there any reason, any sort of a priori reason, any kind of story you'd like to tell about why I should expect that these things would exist in general? Or to put it maybe a little differently.
That's easy.
Good. Do you think of this as sort of an empirical matter or as something kind of a priori? Nature should be full of seeks.
Oh, that's hard. So the first part of the question was, can I give any compelling reason that they should exist?
I don't just mean in quantum mechanics.
Well, in quantum mechanics, I can give it to you, and it's because it makes the equations pretty.
Well,
And I find that really compelling. I tell Osa and I tell some of the students that these things are so beautiful that even if they don't exist, they ought to. And in fact, even if we still fail there, we're going to make them exist.
Okay. So I'll just point out, and I think I can do this because you still haven't answered the question that I think I actually asked. That quantum mechanics itself is pretty. So.
Oh well, no, it hasn't been to me completely.
That's the problem.
No. You see, until I get an understanding of it that just makes basic use of probabilities and doesn't invoke higher level concepts like operators and automorphisms and self-dual cones and homogeneity. So that's right. I have this internal sense that it's getting prettier by making use of these things. And things like the Born rules now strike me as not sort of arbitrary generalizations of the law of total probability, where I've got an extra matrix lying around and it shuffles terms and I've got quasi-probabilities. Instead, it is really just, you take the old law of total probability and you distort it ever so slightly on the outside of the summation. That's why I find it pretty. It may happen for other convex theories. I mean, these structures may arise there, and I say, oh, so much the better for those convex theories, because they have a really simple representation sort of hidden within them. That'd be cool.
So just to be clear, it's not the existence of seeks that you think is so important. It's this slight modification of Bayesian that you
Yeah. I think that is clear. So, I mean, it's a complicated history. Why have any of us been working on seeks? Like Howard has spent some of his brain pulp working on it, and Steve Lemire has used a lot, and Nick has done some, and Robin Boone Cahout, and Marcus. Oh God, Marcus has hardly a brain left. and I was guilty of that as well, because I mean, when Bill showed how to find the dimension 3 solution, got the sense that it's easily posed, and look, somebody can get a low-dimensional solution. It just shouldn't be hard, and then it became a challenge. And all the while, I kept thinking, well, you see, because I like to desire things into existence, I kept thinking they must be useful for something. And I think deep in my bones, what they're useful for is that they let me see the Born rule as an addition to coherence in a simple way. And that's what I really like. So that's a long answer to your short, good question.
I'm glad you said that last thing at the end, because the thing I was about to say was, it seems to me that there are two independent parts to your talk. One is the desire to see the Born rule as an extra kind of coherence rule. And the other one is the let's think about seeks and think about probability distributions on seeks and put constraints down to get quantum mechanics out that way. And they do strike me as independent parts. And I could pursue the latter project without thinking of the Born rule as an extra coherent rule.
Sure.
And it might be useful to do so, because I don't think I said this the last time I saw this talk. Yeah, there is an analogy between What's that?
You didn't see this.
Okay, a talk like this.
There are whole 10 new transparencies
Right,
in
okay.
this.
A version, a precursor to this. Because there's a big difference between things like Dutch book coherence and saying that we ought to have our probability perspective one rule. And it's really highlighted by your really big question. If I didn't have any if a probability that didn't satisfy the Born rule, what bad would happen in a single case? Imagine that we've got some 19th century physicist who's been keeping the freezer, and he hasn't heard about quantum mechanics, and we unfreeze him, and we both bet on an experiment, and he's got classically informed probabilities. And we all bet, what bad is going to happen to him? Well, he might win and we might all lose. There's no guarantee that he's going to have a problem. We think our probabilities are more adapted to the structure of the world because we have all this experimental knowledge that he doesn't have, and we have all this theoretical knowledge that he doesn't have. And none of that is at all like, and we've learned some new kind of coherence. The cool thing about the Dutch book arguments is that if you violate coherence, then you'll have a sure loss no matter what the world happens to be right. Whereas the Born rule, I think you'll agree, is a good rule for using in worlds like ours, and would be a bad rule for using in a world that had classical physics.
Yeah.
So I don't think you need, and the upside is.
Can I address that?
In a moment.
Oh.
I don't think.
You make me reply to too much at once.
I don't think you need an extra coherence rule because as a Bayesian, what I can do is say, all you have to do is start with some priors back in 1890 that attach, non-zero prior probability to the proposition that the Born rule is a good rule for use in a world like us. Conditionalize on everything that's happened in the past century, and you end up with post-theories concentrated on quantum probabilities.
Oh, is that the end?
Yeah, that's the end.
That was too abrupt for me to know.
Oh.
Well, for the big part of your question, I think, at least I'm classifying it as the big part, which is that it looks like there are two separate talks, two separate programs. And, you reminded me of a joke that we used to tell when I was in Boy Scouts about some big tunnel that they wanted to build somewhere in the hills of Texas. And various government contractors came and gave the government of Texas some bids. And, there were like $100 million and $150 million. And finally, these two brothers showed up. And, the Texan roots were, it was like Pedro and Juan. These two brothers showed up and they said, they could do it for $1,000. How can you do that? And he said, well, I got my pick and shovel. And the other guy said, I've got my pick and shovel. And we start at both ends of the hill, and we start digging until we meet in the middle. And we don't have any extra costs, just us and our picks and shovels. And the guy who's in charge of contracts says, well, what happens if you don't meet in the middle? And then Juan says, well, then you get 2 tunnels for the price of one. So that's going to be my reply to you. Now, the way I see this is there are two strands going on. One of them is the Bayesian program, and for the Bayesian program, at least for quite a while now, we've been thinking if we drop the notion of objective quantum states, and we think of them in subjective ways, then we've got to we nonetheless have to make some sense of the Born rule. And the only thing that has struck us is that we make sense of it along the lines of coherence style arguments, but with empirical content. So you're absolutely right. What is beautiful about Dutch book is that it doesn't care which world we live in. And that's one reason I'd say there is no generalization of probability theory. Probability theory doesn't care which world we live in. Apparently the Born rule does depend upon which world we live in. But I want to think of it along the same sorts of lines as coherence arguments, in that the Born rule, I'd like to think of it as an expression of how probabilities should be related. And I'd also like to think of it along the lines of Dutch coherence, in that if I tell myself, oh, consider this experiment, and consider that experiment, consider that experiment, and I find that my probabilities that I've assigned can't be generated from any quantum state, or in other words, can't be generated in this set of relations of probabilities, then I look at that list and I go, oh God, I don't know what to do. Just like coherence doesn't tell you what to do when you violate it, but it tells you something's wrong and you better rethink. So I want to think of the Born rule in that light. That's completely independent of Seeks. I could have thought that in 1986 when I read Bill's paper, if I had known enough about Bayesian stuff. But then there's the Seeks. And I see that with the Seeks, I can rewrite the Born rule in a way that makes it look like it matches up to the other considerations. So here's one side of the hill, here's the other side of the hill. And ultimately, I'm hoping that the two will inform each other. I think that that's what...
There are a series of other people who want to narrow and pick. I didn't like them.
So, I was always very curious about finding the seek in a purely operational way. I'm saying, as a Bayesian, you are also operationalist, right? Because an operator must be Bayesian, right? So, but
I don't know.
why?
I don't know. You know, I keep drawing this picture of a little guy and a little system out there. You see, like Lucian in his program is striving to get rid of that little box. And so in Lucian's program, there are all the operations and how the operations connect together. And from his perspective, the box, having to posit the box, like in his earlier developments, gets in the way of thinking about things clearly from a purely operationalist approach. Now, I keep that box there really for a reason, which is that I'm trying to be the antithesis, to some extent, of Lucian's program. Lucian's present program. I mean, he's not wedded to it for life. But the box does play a role here in that I think the box represents stuff. And I'd like ultimately to do what we did in classical physics and say, the stuff has mass and energy and with bang power. And, you know, something like that. And I like to understand what the with bang power is. So that's not complete operationalism. This is some mixture of the two.
The box is just, you know, whatever is out of there, which is not pure, right? Everything else.
Yeah, but you know, I'm not averse to saying, look, there's Morrow out there, and he has a certain mass, and he has the mass, even if I don't know the mass. But I feel like I can say a firm statement about you. You have a certain mass, and I'd like to say the same of a quantum system, ultimately. So in that sense, it's not completely operational.
Yeah, the point is what is a system. Yeah. Anyway, let's go to the question, which is mathematical. So, sig means symmetric, right? What about trying to get the sig P of m in this way? So, sig P of m's, they are both states because they are rank 1 operators. If you look at them as operators, they are rank 1 positive operators, which can be both states and effects at the same time, right? So I give you for granted a self-dual theory in which the cones of effects and the cones of the space are the same. Right? And now I ask you, optimize something such that you get as a solution of the optimum. Because every time you have a solution of an optimization problem, if you look at for all possible states, whatever, then you find a symmetric solution, right? So what is the optimization which will give this symmetry?
For a general theory.
Or just starting in an abstract way, this way.
Yeah.
I was looking for this for a while. I couldn't find it.
I don't know.
It would be a principle.
It sounds like the sort of thing that Howard might have thought about.
Does the spring function generalize? Does the seeks like realize some values?
This angle, pretty much actually.
Yeah. Yeah. Well, if you have so you have inner products on these spaces. So I know what to do when you've got an inner product. Yeah, you do something like the frame potential.
You have an inner product.
So one way to generate the seeks is to just say you've got a set of states.
Oh God.
Throw that away.
Chris.
Set of states, I.
Right.
And if you form this quantity,
Right. That's an optimum.
to the fourth,
You are optimizing, right?
to the fourth. If you minimize that, you'll get a seek, and where I goes from 1 to d squared. And then you can motivate this by notions of being as close to being orthonormal as possible. So you can do things like that.
Optimal distinguishability, informational complete. This is the principle. It's the best distinguishable informationally complete. Which is also self.
Yeah, I think.
Right. That's
I hadn't thought of it in those terms, so maybe.
that's interesting.
This is fast. Chris, have you thought of using shrunken six-digit?
Yeah.
Would that do? Would that have similar properties?
Yeah, it screws up things. So you see, I can make clean statements about the extreme points of the set. I can just say, you see, my extreme points in my set correspond to extreme POVMs. So there's more I don't know the right technical terms here. But if I had non-rank 1 things, for which we do know they exist, you get something that looks like that generalized Born rule. But then when you try to say, I'm going to get my whole state space just from requiring that this generalized law of total probability, just from requiring that always be positive, then you get screwed up in all sorts of ways. So you get screwed up if you do things like use complete sets of MUBs. They get in the way because the state space is only a subspace in the larger space of operators. And if you use non-rank 1 things, then you don't get the sort of duality between extreme points of one set and extreme points of another.
Sharpness that comes out from having rank 1 project?
Yeah.
So we were running out of time. I just want to take a few more questions. Michael and then Philip.
I was interested in your condition for the probability, the triple product of the probabilities of the symmetric part of CJ and K. It looks like the other somehow the commutator structure doesn't appear to characterize the mature state. So the sort of convex part of setup. The real remark is maybe you could have some action just looking at your product of three independent probabilities is what it looks like. So you've got an expectation value of the three systems as well. You say that the expectation value of that symmetric three system is constant.
Yeah, I've wondered whether one can give a meaning to that CIJK. If you
Yeah, you can. It's structure constants for the algebra, but it includes the anti-commutator as well.
well, you can use those as structure coefficients for a Jordan algebra, for instance. But what I meant more particularly was like if you look in the statistical literature, you find this combination of probabilities with an interesting 3-tensor flying around. And there is something called Amari's skewness tensor for a probability distribution. And I tried to fathom that literature, and in the end I just got frustrated and couldn't figure out what was going on. So it looks like quantities like this might have arisen somewhere in classical statistics as a characterization or a characteristic of statistical manifolds. But I don't know. But then there's the other aspect of it, is like Nick was just talking about. You can take that Cij(k) and you can generate a Jordan algebra from it. So use that as structure coefficient for Jordan algebra. And so, it is kind of interesting that there is and very directly, so there's a connection between this convex shape and some Jordan algebra, or the Jordan algebra. You can get anti-commutators from this quantity. Why they should be connected? There's probably a deep reason, but I don't know how to exploit it.
This last question.
Just quickly, when you apply Bayesian laws to a double slit experiment, you end up with something which is not the classical probability sum, right? You get P1 plus P2 plus interference. An interesting point is that if you take a suitable average, say you don't know what phi is, and this is a uniform pi over phi, and you sort of take the average of that quantum expression, you find that on average you get that P12 equals P1 plus P2. In other words, you recover the classical sample on average if you take the average suitably. And in the thing like the derivation I described yesterday, the whole of part of the derivation can be replaced by that requirement. You can basically get rid of the two complex cases you don't want by imposing this average requirement.
Mm-hmm.
So in that connection, I was just wondering about your situation. You get something which is not the probability product group. You get a variation. So I'm just wondering, and as you said, you can't really seriously take as a variation of the normal probability because there are additional conditionalities which you haven't built into the notation. So I'm wondering if you could impose any kind of average value constraint on your any expression you get, whether that be useful. And related to that is that
what would you average over? The seek in the sky, or the measurement on the ground, or something else?
So in other words, if you've got a variation of the probability, is there any situation you can conceive of where the variation has to collapse
to the law of
the classical one?
Yeah, I don't know. I haven't thought about that. I don't know. I mean, maybe it's conceivable, but I just don't. I don't know. I mean, somehow you'd have to have it be the case that I tend to think you probably, if I average over the top guys, I don't have any good answers for that.
No, it's just a suggestion, but it seems to be quite possible.
So something to talk about over lunch. Comes up right now. Let's thank Chris again.